Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. This is episode 24. We are still working on the Xenowing, and we are still working on Kaze, my Rust HDL. Just like last week, been making a lot of progress. Maybe not so much as last week, but still going strong. One of the things I followed up on is I made a pull request at the end of the last episode where I fixed some issues in the RISC-V compliance suite. That one was rejected, but only because it was in favor of one that solved the original problem that we had and also a bunch of other issues. And it looks like they just merged one earlier today. So I was going to dive right into Kaze, but I actually kind of want to really quick update the test suite for the Xenowing. So I'm going to do that really quick. So going to Xenowing here. So if I just do make test now, it will run... It runs the compliance suite like we had before, but now there's no kind of issues that we had last time. So we can see that there's verbose output from the tests, and nothing actually breaks, at least for the tests that we support. There's still the 4 tests that we don't do anything with, that I manually just disabled on my branch here. And that's the eCall, eBreak, and then these misaligned stuff. So that's pretty cool. So hopefully, I don't think I have anything in Xenowing that's not published. Yeah, I don't. So if I go to tests, RISC-V compliance, we'll fetch upstream, which should have some fixes. And then we can just rebase on that. This probably cleanly applies. And it did. That's great. So let's go ahead and I think it's all my stuff at the top, so we'll ignore that. If I do a make clean out here now, should be fine. Now I do make test. We should see basically the same thing. And one thing I actually think is going to be fixed now too is I don't think the AOIPC test is going to overwrite the code section anymore. We'll see if that's actually the case. And of course, I'm building Rust, so my stream is going to become real crap for a minute. It's taking surprisingly long to build, actually. This normally isn't this slow. But maybe it's because I'm streaming and doing some other stuff too. All right, so now it's running. Okay, so it does... This AOIPC test still writes over program ROM. Fine. So we're not going to go ahead and disallow that in the simulator again. By the way, hi to R2 and Desu used. I've got a screen I need to get rid of, so maybe I should donate that to you, Desu used. By the way, congrats, Drew, on getting back into streaming. So this, I think we just want to force push to master then, because we've seen that it works. And then I'm gonna do the same thing here where I'm just going to commit. Like that, push that. So that's pretty cool. So now let's get back to what I'm actually working on. So like I mentioned earlier, like I've made a lot of progress on I don't know if I can work with this big a font today. We'll see. Anyway, I made a lot of progress on Kaze, and in particular, the big missing feature now. Actually, let me kind of recap what I did. I don't feel like I did that much, but I know I did. Oh yeah, there was actually a fairly large change in the last week. So what I did is I added implementations for subtraction and all the shifts for signal. And that actually was kind of a lot of work. I had to refactor binary operators in the simulator IR to kind of simplify a lot of the logic that was in there. And then that actually made shift natural to implement, and then the other shifts were kind of trivial after that. And then that allowed me to, those features allowed me to move the ALU into the RTL instead of in the simulator, which was actually pretty cool. So now if we go into Xenowing, the RTL project is just a Rust project now. And before, I had the CPU export all these signals for the ALU, which is just the left-hand side, right-hand side, op mod, and then it'll get the result as well, which was an input. But now it actually routes these to an ALU object, which is in the RTL itself. And that is pretty basic. I still don't have like a switch case kind of construct or a match case kind of construct, so it's just a big bunch of if statements. Hey, Chief Detector. But it's still simple. So this is the whole ALU now. So it's basically just checking the op against several different hard-coded values. In fact, there's 8 of them. We just check all 8. And then in some cases, there's also this op mod value, which I think is only used to make add into a sub. And down here, it's used to change a shift right into an arithmetic shift right, and that's basically it. Everything else is really straightforward and was already implemented in Kaze, so that was the only thing that was missing. And it ended up being, the right refactoring. So I was really happy that I was able to get this in. Now, the one thing that's still missing to move the entire CPU into Kaze is the register file, because Kaze doesn't have a concept of memories. It has the only state elements that it supports right now are registers, and then I'm working on memories. And memories is kind of one of those things that I normally would like to defer, because like a memory is a really easy thing to break out and then instantiate outside of some RTL. But as we get into buses, we're going to end up with a bit of memory per bus, basically. I drew this out in my notebook, but I haven't done a proper diagram of it yet. But I think originally I had some PDFs of like the memory topology, but I kind of have to revisit this. So I'm going to do a quick stab at it here, and I'm probably going to miss out some details. But we actually have a couple boxes here. So my CPU is called Marv, and I'm making a different box that says CPU because this is going to be like the interface of the CPU. And then there's a few other at this level. So there's going to be the display hardware, and I don't remember what the name for that was at the moment, so we're just going to call it DISP. And then these two are both going to drive... Actually, I think there's another one too. Yeah, because there's also the DMA, which is going to be... We'll put it out here, for example. It doesn't really matter that I get these exactly right. What is important is that I get the connections between them and I'm able to communicate the problem. So down here, there's going to be a system bus, which we're going to call sys. And after that, we have things like RAM. ROM is down here. And then we've got like LEDs or UART, for example. And we also have like the GPU, which is particularly important. So things like the GPU and RAM, we want these big wide 128-bit buses. And it might be that that many bits is actually going to be a nightmare for actually compiling the thing or getting it to work on my chip. So if that's the case, then we're going to drop those down to like 64 or 32 bits. But we're going to assume that it's going to work until we actually run into a problem, because I think that'll be a relatively easy change to make later. So ideally, we're going to make it 128 bits wide. And that number comes from the nominal width of the memory controller that we have on my current board. It was 64 bits on the old board, but it's 128 bits on this one. And we want to try and maximize that, because then we can maximize bandwidth to and from RAM, which means all the things that we're doing on like the GPU can actually move into and out of memory a lot faster. So with the system bus, I'm going to have basically a read port and a write port that connects to all of these. So we can represent that by doing arrows in both directions. So generally the masters are up top and then the slaves are down below. And then I've also kind of ordered this, well, we'll forget about priority for now. So these are really straightforward. You have like the sys is kind of this arbiter that's going to arbitrate this stuff. But you can kind of, from just this stuff down, the sys and below, you can just imagine the sys is the master and all these are the different slaves. And so each one of these is going to have its own read and write port. And all of these would be 128 bits wide. There's a few more signals there that I'm kind of working on documenting how I want that to work. So we'll ignore that, though. It's not really that important. But each one of these has all these signals. And is this how I wanted to do it? Maybe the DMA actually has two because it wants to read and write at the same time. Well, actually, it works because we still have read and write ports. So I think everything's okay here. And now we get to the actual drivers of this. So the CPU is going to have a write port to the sys and a read port. And then the display hardware is going to have a write and a read port. And this is actually, this top part is really kind of where it gets more complicated. Because if there's a single master, there's also this, which is going to be a 32-bit bus. And so that's why the CPU interface is separate from the CPU, because the CPU only exposes this 32-bit read-write thing. But then for the CPU to interact with this bus, it needs to kind of bridge the gap between this 128-bit interface and this 32-bit interface. But yeah, essentially it's this multi-master thing that's going to be the primary driver of the issue that I'm trying to outline here. So let's pretend that there was just one master and it was the CPU, and let's say it issued a write. So a write is really easy to handle because you get like an address and some data, and then the CPU kind of just does fire and forget. There is a bit of feedback here, like there needs to be a handshake to be able to access this bus. And that's for things like if the RAM is busy doing refresh cycles, we need the CPU to wait for it to do that. So there needs to be some handshaking throughout all of this infrastructure. Like the buses in this system are actually going to be fairly complicated, but I think they'll be easy to test with the rest setup we have. Anyway, write is basically just fire and forget. It goes into here, and based on the address, we see if the appropriate slave is ready or not, and we propagate that signal back to the CPU. If the thing it was writing to was ready, then it fires off the write, and we're done. So that's great. Reads, however, are a bit more challenging because we need to fire off the read, which is kind of like a read request, and then the data is going to come back at least one cycle later. Again, we have to make that kind of asynchronous interface. I'm going to call it asynchronous because even though it's like on the cycle clocks, it's we don't know how many clocks it will be from when we issue the read until we get the data back. So it's asynchronous in that sense, and we have to design around that. So we issue the read request, and then it will go to the appropriate slave, and then the slave will eventually have some data ready and sends that back to the sys, and the sys relays that back to the master. So in a single master case, that's really simple. However, in a multi-master case, you have to handle the case where different masters are issuing things at the same time. So you actually need some arbitration here. And considering just the case where there's two of these is basically the same as any other number. So if we ignore the DMA, for example, we just focus on the CPU and the display hardware. Now, I know for a fact that I always want the display hardware to have priority over the CPU. If the display is reading out pixels that it needs to get to the screen, it needs to do that in a timely manner, so I'm always going to give that priority. And in fact, actually, the display is never going to write, so I drew this a bit wrong because it's only going to do reads, which isn't terribly important, but will be correct for the actual system. Yeah. Anyway, so the case we have to worry about is if the CPU is trying to interact with the bus at all and the display at the same time. And in that case, it's actually pretty easy what we do. We just tell the CPU that the bus is busy, even if it actually isn't. And then the display hardware is able to actually access the peripherals as if just in the same way that the CPU does. But there might be a case, there probably wouldn't be with the display hardware, but maybe for the CPU and DMA or something. I'm not entirely sure, but it might be that the CPU and display can like alternate accesses. It doesn't really, I don't think this system actually needs to cope with it, but just to make a general bus that could cope with that, I think is a good exercise. So let's assume that we have two masters that could actually just alternately issue read requests. And if that were the case, again, firing off the read request is not that big of a deal because every other cycle we would just give the bus to either one of these masters, and then they would just fire off the read requests. But the returns are actually where the problem arises. So let's see if we had I'm gonna use D and C. So D is going to be a display read, and then the CPU is going to do a CPU read. So let's say over time we had these reads, DC, DC. And eventually we're going to make also the assumption that these reads are going to return in the order that they were sent, at least to a given peripheral. So if, or these reads are going to be issued in order, and they're all going to return in order, which is something that we also kind of have to, might have to do some work in order to maintain that. But I think it will be the case from a given master that every read that it issues, it will get the data back, and I think that will be easy to make sure that's the case. Anyway, so let's say we had some case where the display hardware sent a read request, and then the CPU did, and then the display did, and the CPU did. And at some point later, this data is going to start coming back, and so we can, again, say DC, DC, sometime later. Now, the system bus needs to know, once it gets this back from one of these slaves, it needs to know which master that data needs to go back to. That's kind of the issue. And so the way that we solve this is actually really easy. We maintain a FIFO that literally contains this information. So whenever we issue a read, we issue the read to the corresponding slave, and then we also push a D into this FIFO. And then we do the same for C, DC. And then as soon as we start getting the data back, we're pulling off of that same FIFO because it's going to return in order. So once we get some word from one of these slaves, we pair that data with the next entry in the FIFO. And then we send it to the correct master depending on that. So it's really that simple, but the thing is that we need to support that at all levels of this hierarchy. And the other thing is that we need internal memory to be able to create this FIFO and actually store this data. That's kind of what I'm getting at. We could actually create that memory by hand with registers, but that's not ultimately what we want to do, and it's not what we want to describe in the Verilog that we're going to generate from this. So that's a really long-winded way of saying before we move on with like anything in the XenoWing, we really need to have the HDL support memory, support internal memory. Hey, love like Semtex. But yeah, the actual hierarchy of this, or the topology of this bus, or these buses, I should say, I needed to document that as well. And I have started writing a document that outlines the actual transactions, how they're going to work. And it's not terribly complicated, but it is something that we're going to want to do a lot of testing with. But again, because we can generate these Rust simulators, it should be really easy to test these. Yeah. I'm trying to think of, is there actually a case? I don't think there's ever a case where this stuff could get out of order. I guess in theory it would be possible if like this display hardware issued a read to ROM one cycle and then RAM the next cycle, and then the ROM returned the data sooner. That would be a problematic case, but then I think we need to just design these individual systems such that that would never actually be the case, which I think is really easy. I think that just will never happen. The CPU, I know it won't do that because the CPU always waits to get data returned before it issues other read requests by design. So I think we'll be all right with that. Otherwise, we basically have to stall the whole system whenever we issue a read until we get some data back. But we're just going to do this basic FIFO approach, and I think it's going to all work out. Happiness and rainbows. Anyway, so that's what I'm working on today is these memories. And I'm not 100% sure about the API that I want, but I am starting to settle on something that I'm okay with. So I looked at what Chisel did, and I looked at what Spinal HDL did, and both of them have docs that say like memories are kind of hard to abstract, and they are, because there's a lot of different kinds of memories, and it can differ between like ASIC and FPGA. And so I'm taking the very pragmatic approach that I'm just going to make a solution that's good enough for my needs right now, which is basically it's all synchronous, so all the data will come out a cycle later. In fact, I actually have a diagram that I made, a signal timing diagram that describes this kind of memory. Let me pull that up. So I think it's a bit easier to describe visually like this. Come on, please load. Yeah. Oh, come on. I sent it to some people on Slack, and now I'm pulling it up there, and it just keeps eating shit. It's making me really annoyed. Anyway, here it is. Okay. So the idea here is that there's these different signals. Actually, this actually shows the bus signals, so maybe this wasn't even correct. Okay, let me find the blog post that talks about it, and then I'll look at this. Because it's not exactly what I'm thinking, but it's close enough. All right. Good enough. Okay, so this is just a blog post about designing memories in FPGAs and how, if you want like multiple read or write ports, how that can actually be implemented. And we don't care too much about most of those details at this high level. But what we do care is some parts of here that are important. This has 2 write ports actually, and we can basically just ignore the fact that there's 2, so we can pretend that this second write request is on this line. In fact, I can maybe, well, I can't really hide it because of some important stuff down here, but this last part we don't need to think about. So the idea is that there's, for each of these write ports, we have an address and then the data that it wants to write that's going to go into our memory, and there's also this enable line. And again, I'm only going to support one write port, and that's basically to avoid cases where both try to write at the same time, and then what happens? In this case, they're trying to say that it's undefined, the value that you get back. But again, like if we consider the one write port case, so let's say this is just showing that the way you do a write is you have this enable, and then the address and data, it will write this data to this address. And then sometime later, as you can see, they issue another write. And then reads are really simple too. You put enable and then the address, and then on the next cycle, the memory will return whatever data was at that address. And you can see we wrote to address 2 with hex 55 here. And then so later when we read from hex 2, we got the data 55 on the next cycle. And the other important thing here that we're also taking is that if you try to issue a write and a read on the same cycle, you get the data that was written in that cycle back on the next cycle. So these are called read-through memories, synchronous read-through memories. And most FPGAs support this. So we're going to, again, single cycle memory reads. And that'll just simplify a lot of timing. And again, a lot of FPGAs have that built in. There's some equivalent Verilog that I found here, which basically looks like this. So if you guys are familiar with Verilog, then it's easy for me to explain this. If you're not, I apologize. I'm not going to spend too much time on it, but it doesn't really matter. So this is what it would take to infer this kind of block in FPGA. The point is that you have the RAM itself. In this case, there's 32 entries, which I don't know why. Yeah, there's a 5-bit read address, and the clock is going to be 100 megahertz. Deep detector. By the way, hi, Mad Moose. So the issue is, the behavior is that whenever there's a positive clock edge, if the write is enabled, we're going to write that value, and then we're also going to latch the read address, and then at any time, we're going to make the data out reflect the RAM at that address. And this matches that behavior exactly. Like if you read this sort of sequentially, it's easy to see. But this does actually match exactly the behavior that I described. And the key part here is that it latches this read address, because if you leave this part out and then you always assign the RAM to whatever the output to whatever the read address is, and the read address here is just an input, then you have asynchronous reads. So like in the middle of a cycle, as read would change a bunch, as this address might change or things like that, then the value is supposed to reflect that immediately. And we're kind of saying we don't want that. We're kind of saying that we're latching whatever the address is, so that the output here is only ever going to change every cycle. And And that's kind of an important distinction. That's kind of subtle. But yeah, we're going to adapt that behavior. And in fact, that Verilog is more or less exactly what we're going to have the compiler generate once we actually do generate Verilog, which I'm still postponing. It'll probably be postponed until after I do all this bus stuff, and then I finally want to test it on the FPGA. And then I'll just write the Verilog output probably relatively quickly. But I think this is like, this memory thing is probably the last major feature that's going to go into Kaze before it's, I don't know, before we stop working on it as much, I guess. So it's kind of a good thing to get this in and see what it looks like for Sim and what the API looks like, and then the Verilog generation should be, I expect, relatively trivial. Anyway, I started implementing this, and the API looks something like this. So I'm adding this mem function to a module, and you give it a name, which is only going to be used to generate errors, because there's a lot of ways that you could use this wrong. And then you give it an address bit width. So in this case, I'm only going to support power of 2 memory sizes. Again, that's a simplification that I'm just deciding to make. And then you give it an element bit width as well, which is the width of all the elements in the memory. And then that's going to return a memory object. And I think there's no public fields on this except some of the methods. So you can specify initial contents. So if you just want to use this as a ROM, you would specify initial contents, and then you would build a read port. And to build a read port, you have to give it a signal that represents the address and a signal that represents the read enable for that specific read port, and it will give you a signal that represents the data coming back, which is going to be valid on the next cycle after you issue a read. And then write ports are created basically the same way. You give it an address, a value, and an enable, and then it doesn't return anything because you've just created the write port. And I think I'm going to have it such that you can only create one write port, and also you must create a read port. Otherwise, you're just putting memory into the void, and that's not useful. So that's going to be an error as well. And then it's also going to be an error if you need to either add initial contents or a write port. You could add both, but you need at least one of those to be a valid memory. And that covers all your cases. So if you just want ROM, you'd only add a read port and initial contents. If you're reading, that's basically just uninitialized memory, that has to be a mistake. And then you also don't want to be able to write into nothing. I think I mentioned that already. But then you can also add multiple read ports if you want. So I'm going to have basically an unlimited number of those. And that might be a bad idea, but I don't know. I think that's fine. And then I think it's okay also if you want like a read and a write port and no initial contents. That's okay, because that's essentially just uninitialized memory, but you can still write to it, so you get some kind of correct behavior. And for example, the register file in the CPU is actually going to have initial contents. It's basically going to clear all the registers. It technically only needs to clear the register 0. And we also could implement that differently. We could actually have 31 registers and then another one that's just 0 all the time. But the easier way to implement this on FPGA is to implement a 32 word 32-bit memory and then have its initial contents be 0. So that's how we're going to implement that. So we're going to do that, and then we're going to have a single write port and then 2 read ports. So that's what we need for our internal memory. And for those FIFOs, we need 1 read port, 1 write port, and that should be it. And I think the FIFOs then will always have at least 1 cycle latency. We'll kind of flesh that out a bit more in testing and see what we can do for that. But it should all just kind of work pretty nicely. So I've started implementing this. I started with a test, and I keep refactoring parts of the simulator compiler to kind of make this a bit easier. But essentially, we have this mem test module, and we create this memory called mem A, and in this case, it's 4 bits wide and has a 1-bit address select, so there's 2 words. And then this will, let's see. Yeah, we create a write port, and then we just route some inputs into it, and then we create an output based on this read port. So it essentially just breaks out, it creates this memory and then breaks it out in a module that we'll be able to test with. So this is basically, again, just like the simplest interface we can do with a read and a write port. And we'll test like initial contents and all that stuff in other tests, but this is the first test I want to get working. So let's see. I don't remember how far I got with this, but I'll just keep going. Oh yeah, okay. So I did a couple things. I think this needs to be changed. Maybe I did this actually. Yeah. So the way that this compiler works in Kaze is let's look at the simulator, because there's essentially going to be a simulator compiler and a Verilog compiler, and I'm keeping them as separate compilers because they both are going to work fairly differently because they're generating pretty different kinds of code. And you can kind of think of the graph that you get internally in the Kaze API as like the front end to this compiler anyway. So this is just a pretty natural split to have different backends. And they're going to share some code. For example, the validation paths can be shared between them, but right now it's only used by the simulator compiler. So when we generate a simulator for a given module, first we validate the module hierarchy. So we say that this is going to be a top level module, and then we validate the hierarchy from there. And that's going to, like I said, that's going to be used by both of the compilers. And this does things like it looks for undriven registers. It's going to also look for those invariants I mentioned about the memory. It's going to validate those then as well. It also detects recursive module definitions, and it also detects combinational loops in the graph, which are unfortunately possible to construct once you have inputs and outputs to modules. So we actually need to detect that. And then I have a bunch of tests that test for all these cases as well. So we'll add some of those invariant checks for memories too, as we get to that. But then once that's done, then we go through the graph, and we start at the outputs, and we work kind of backwards into the module. And we trace through the whole graph, and we sort of pick up all the registers that were reachable from those outputs. And then once we've gathered all those, then we have, I think I've called these state elements because we need to gather registers, and eventually we also need to gather the memories. And I think I do that now. I'm not sure. I don't remember where I left this off yesterday. But the point is that you gather all the state elements, and then we go backwards again from the outputs and from the state elements' inputs. And then we trace the graph back again, and that's where we actually start compiling code. And the important part is that the simulators here, I wonder if I have an old one generated. Yeah, I do. So the interface of these simulators, you get, let's see, I want to find one. Okay, so these are just really basic, purely combinational simulators. So here you get a struct where the inputs are fields. And then you have this new, which just creates an uninitialized one. And then you have this propagate method. So the idea is that you would write all the inputs and then call propagate, and then the outputs will reflect the values that have gone through this piece of logic. So that's essentially what we're compiling. We're going to compile all the assignments that are in this prop function. So you can see back in the simulator compiler, there's this prop context, which just holds all these assignments. And we compile signals sort of into that. And then, we compile signals to assignments that go into that context. But there's actually two other contexts. If you have state elements that are important, we have this reset context and then this pause edge clock context. So these are methods that are added if you have state elements. In this case, there's a couple registers. And so propagate works just as it did before. It propagates inputs to outputs, but in that context also it propagates outputs of registers to where those would go as well, which could be to outputs or to like inputs to other registers, and propagates like inputs that. So it basically propagates all the combinational logic. Yeah, signed. That's great. And then also there's this reset method, which if any of the registers had default values, which they might not, that's optional. But if they did, or similarly with memories, the initial contents, those are going to be filled out here in reset. And then there's this pause edge clock method, which is actually going to tick the clock. And all that really does is it sort of latches all the values. So you can see in this propagate function, we have a couple registers, and it doesn't actually update the values of the registers. It updates what their next values are going to be. So it sort of updates the inputs to the registers, and then when you do a pause edge clock, it ticks so that the outputs reflect the inputs. And again, memories are going to work exactly the same way. So that's why I've kind of put those under the same umbrella in the compiler as state elements, because they're going to have very similar behavior and be compiled very similarly. So that's kind of the idea behind this compiler. And the Verilog one is going to be a bit simpler. It's still going to traverse the graph similarly, but its code generation is going to be a bit simpler because it's already almost Verilog. So that'll be a bit simpler, but it will still be similar. So yeah, so we validate the hierarchy, we gather all the state elements, then we compile coming from the outputs and also coming from the state elements. So basically we figure out signals that route to the outputs, and we output all that stuff, and then also the ones that are inputs to state elements. I've said this like 3 times, but that's what we're doing. And then after that, we actually write all the code. And so then we generate these inputs, we generate the outputs, and these are fields on the struct. And then, yeah, if there were any registers, we generate definitions for those. And then here, if we had state elements, we also generate some code into these reset context and posage clock contexts. And then we actually write out those contexts if they have anything in them. And when it writes these contexts, it literally just writes out all those assignments one by one. So it's a really straightforward compiler, which is kind of the point. That's one of the ways you keep these things robust, is you keep them simple. So yeah, pretty happy with this. But yeah, it doesn't support these state elements quite yet. I think I did this part where we gather them, and I think that supports memories. I think it's not terribly difficult, because essentially as we're tracing back in the graph, we look for signals that represent, in this case, a memory read port output. And once we hit that, we see if we've already gathered that state element or not. And if we haven't, if we have them, we just return. If we haven't, then we need to gather that, and then we also need to trace its inputs. And I have a note here that I don't think we need to trace all of the inputs. We do need to trace the write ports, but the read ports, like we don't need to trace the read ports, the other read ports than the one we actually hit, but there's some extra state to keep track of if we want to do it that way. So I've just ignored that for now. And then the compiler itself, what I call compiler here, really is the expression compiler. And this is the thing that's actually going to output expressions into the different contexts. So in this case, we've traced back in the graph, and now we've reached one of these read port output signals. So we have the memory that's coming from, and then we have the address and the enable for this particular read port. And so to compile that, we need to compile a signal for the address value, and we need to compile a signal for the enable value. And then we're going to return a conditional. And so essentially what I want to do here is if enable is not true, then I want to have some default value that's like all Fs or something. Really, it could be anything, but that's the arbitrary value I want to choose, because I feel like that's going to be easier to pick out than a bunch of zeros. So we're going to want to fix that in the test. And then when it's true, we need to actually output an expression that represents reading from that memory with address as value. So that's what I'm doing here. I'm returning a conditional where the conditional is enable, and then we have this when true and when false value. And this expression IR is literally just this IR that's made specifically for outputting Rust code for the simulator compiler. So there aren't many concepts here. There's an expression, and there's just basic stuff that you would find in Rust. There's these, I call this binary function call, but I could have just called this function call with this many arguments. Maybe that would have been better. There's a unary member call, so maybe I want to unify those, but it doesn't really matter. You can have a constant, you can have an infix binary operator, you can have a reference, which will refer to some name in some scope, and the scope is either like member or local, I think. And then you have ternary, which is what this conditional is going to compile down to. In fact, I think that's what we spit out here. Spercond. I think this should be ternary. I think this is wrong to write it this way. And then, yeah, unary operator, all kinds of stuff. So again, really, in terms of compilers, really basic, but I think Rust is a nice language to write this stuff in, so I'm just kind of talking about it. Hey, Dark Second, thanks so much for the sub. Really appreciate it. So yeah, so we want to output this ternary, where the conditional is this enable signal, and then true. I think we're going to have to extend the IR here, because one of the things you see isn't here is like an indexer. So essentially the memory I wanted to compile to a field on the struct, and that's going to be an actual array of probably a fixed size, since we already know the size at compile time. And we're probably going to make that a boxed array, because these might be quite large. And then the data type that's going to be is going to be determined by the bit width. So there's some things in the compiler for getting a type of a value from a bit width. So I have this value type thing, and then it supports just a handful of values that we will actually ever output. And you can get a value type from a bit width, and it'll give you just the unsigned one. And then if you want a signed one, you can do 2 signed on that. I might actually split this into unsigned and signed types specifically, which I think would give me a little bit of a nicer experience in the compiler code, but haven't gotten to that yet. But anyway, that's how we're going to determine the type of the array. And then the reset context is going to contain code to set up the initial values, if any. And then the pos clock is going to contain code to sort of latch the read address and also perform the write if that was enabled. And then the propagate context is going to contain code that just returns, just does array lookups into that array. And we don't really need to do any validation like bounds checks or anything in the generated code, because we kind of we have checks and limits in what the API will handle, like at the top level. So all that validation is already done. So by the time we ever get to like this code gen stuff, we're assuming the graph is valid, which is why I have to-dos for like a lot of tests that we can do to guarantee that the implementation will always ensure that those invariants are not invalidated or not violated. There we go. A lot of words. So here, this when true, I think I did this ref, but this ref is actually not enough, because this needs to be a lookup. So actually we need to add some array index to the IR, and I'm just going to call this array index. And let's see, I don't know, what did I call this for? I called it the target of, for example, a unary member call. So I'm going to call that target here. So this is the array that we're going to read from. And so there's an expression for that, which is what that ref is going to be that's there now. And then we're going to have an index, and that's also going to be an expression. So really basic there. And then this compiler needs to spit out not a ref, but an expr.array index. And then the target is this. And then the index is address. Struct module mem. Found struct signal. Value name. Oh yeah, because that's, yeah, so I don't gather the memories quite correctly yet, but I'll fix that soon. And then when false, I think I'm going to do this as a to-do. And then for now, we'll just do a constant. We'll do this properly shortly, but I mean, we could do that, Mad Moose. In fact, if I wanted to output unsafe code and avoid actual bounce checks, I could do that. And I would actually be comfortable doing that because, again, all these invariants are ensured by earlier compiler passes. So I would not be above that. What did I do for constant? That's also in the IR, right? Struct constant. Is that not here? I thought it would have been down here. Yeah, it's here. Oh, yeah, it's enum, yeah. So we can do, I don't know, constant bool false for now. This is going to be wrong in a lot of code, but we can sort of fix those issues progressively as we get stuff building. So yeah, do this. And then, yeah, I want to fix this issue first. So when we gather these state elements, I mentioned that I do gather the memories, but I think I just insert this reference to the memory itself, which is actually not what we want to do. So when we gather the registers, what we do is we generate a new name for the register. And I think we can do the same here. And then I also generate some names for fields that I'm going to add later. Yeah, I could do that too, Medmus. Either way. But yeah, I generate these names and then I insert a struct that represents those names instead. And then also that has a reference to the memory too, in case we need that for generating code. So I want to basically do the same thing here. I can do exactly this. Oh, I actually think I can remove this derived clone, by the way. In fact, I think I can remove that on a lot of things. A derived clone. Signal has a bunch of those. Yeah, because I used to have before I separated these two passes in the compiler, I needed to clone something because of lifetimes. Clone, that's what I'm looking for. And I actually don't need to do that anymore. I think these unary operators I still want clone for. Is that it? Do I need clone on those two still? Let's see. I think I do, though, because I think I move these around a lot. We'll leave those ones, actually. But I think there are these other ones in IR with clone. Maybe that's okay, actually. Maybe I remove the ones I didn't need already. Yeah. I actually don't know if I need clone on this stuff anymore. Whatever, it doesn't matter. Mr. Tall, yeah, I know what you mean, and I always forget, and I had that exact same experience at work like the other day when someone else used it, even though I knew it from before. So yeah, I'm so happy to see that every time. Hey, Alkama, thanks for the sub. Really appreciate it. Yeah, I don't think that needs clone anymore, so we'll get rid of that too. And then we'll do this. So struct mem, and we'll just do the same pattern where we take the same name for all this stuff. So graph mem, and then what do we want? We want the storage name, I think, and the read adder name. I think those are the two things that we need to generate. Let's actually call this mem name. Am I your only sub, Alkama? I can't be. Oh, you only sub to me? Yeah, that makes more sense. I was just like, do I sub to people? I should do that, by the way. But yeah, I really appreciate it. That's awesome. Let's see. Yeah, so now in here, this hash map for the mems needs to be this mem. That's what we want. And I think... yeah, well, this. That's what we want. I think, yeah, proper value type, and that's what that means. So we can get rid of that to do. And then we need to construct it here, which is going to be mem. the memory, and then we need to, we'll do this exact same thing here. Yeah, and what were the names again? They were mem name and read adder name. Let's do this. And data name becomes mem.name, and this becomes self.mems.length. Lemems. And the name is private on mem, and that's because in here, this also isn't in the right place, but it will be. We want to make this pub crate, keeping everything private, but we need to access it in other parts of this code. So do that, and then yeah, we need mem name and read adder name. Oh, that's awesome, Ferris. It's actually oh no, that's awesome, Alkama. I'm glad that tool inspires you. And that's a good idea to have an FFmpeg exporter. It's really a pain doing even using capture. As good as capture is, it's a pain. And there's my wife laughing at me from the other room. Fantastic. Yeah, is it in Rust? That's awesome, if it is. Otherwise, I'm still interested, because I think that's a great idea. Yeah, I did. Oh, she's at work watching. Oh, that's nice. That's so cool, though, Alkama. I would still love to see it, because that would be a useful feature in our tool. It looks like we actually might do some work in our tool as well soon. I might stream some of that. We'll see. We'll see how we end up divvying the work, because Darth Shader, every so often he shows up and does some awesome tool work. He's basically responsible for the fact that we have packed fonts in our tool. And it looks like he wants to help out with some of the node stuff. And it wasn't really something we were going to consider for a while, except Solskogen announced that it's going to be their last one this year. And so then, of course, we're considering doing something. So we're going to look into the tooling changes we want to make. And if stuff works out, then we'll have something. Otherwise, we won't. So we'll see. Congrats on the Dremel and the Vice, Dark Second. I love my Dremel, but I don't have enough opportunities to use it anymore. Yeah, it breaks my heart too, Alkama. But man, they had a good run. So I'm very happy about that. And I would love to support the last one as in some way that I could. Oh, that's really cool, Dark Second. Yeah, no kidding. Right, so now we need, in this case, we need to make an array index, right? And then the target is going to be not the value name of the memory, but it's going to be mem name. And also, I totally just noticed, wait, what? Did I not do this right? I did a signal for this. Yeah, I think we need to shadow key here. That's what we want to do. But actually, we can just do this. Because then key is going to be context mem. Yeah, that's what we want there. And then this is actually wrong too, because this would index it with the address, and that gives us asynchronous reads, not synchronous. So that's actually also not what we want. In fact, this might actually be kind of interesting, because previously, no, this is what we want. And we actually don't want the address. We do want enable. We actually don't need the address here. Okay. Because instead of the address, we actually need another ref here. We're going to shadow mem here. Get rid of the address. Mem is this guy here. Because we need to use the latched address here. That's important. And let's also just take a reference here. That's fine. And then mem name is not what we want. We want the read address name. And those are going to be members. So this is what we want. Great. So this is what we want to do for this expression. And the only thing that we'll want to change later is we want to use a better default value. So we'll get there. We'll get there later. But yeah, so that's what we want here. And then at the top level stuff, we're going to want to generate the things to make this valid. But I think this might be enough to make it compile. And I want to do that because I'd rather see it generate bad code than make it work all the way. Okay, yeah, so now it actually broke because we added that IR array index thing. And now we have to implement that. So we're going to go here. And I think it's just this write function. So this is basically trivial. And so once we have an array index, then we do target.write, and then we'll append this, and then we'll do index.write, and then we'll append this. And this is going to be expression array index. Okay. So I think this will actually work. Actually, did I do .test here? That's not what we wanted. We want to actually just do in the Kaze sim tests and do cargo test there. And this should fail. This should not build. And there we go. So what happened is, since I use a build script for these sim tests, it did actually run that, and that worked successfully. But then it tried to compile the output, and that didn't work. And so if we look at the output, this is the same file I had open earlier, which might be the right one. Yeah, it is actually. Here's the generated code that we got. So we had these things that we broke out here, and then the outputs, and then it generated this code for prop. So in this case, it said the read data is, if it's enabled, then we go ahead and read out of the memory. Otherwise, we return true. So this is exactly what we want, actually, except now we don't have these fields generated up here. So we need to generate that, and we also need to generate the reset and other contexts as well. In fact, I'm going to skip reset for now, and we're going to wait until we write a test that has initial contents before we add that. The other thing that I'm noticing here is that to index, we actually want to cast this to a usize. Now I'm thinking that I actually want to do that here. Which is me being a little bit lazy, but I don't, because I actually do support casts in this IR, but I don't have any way of describing the usize type, and I don't want to start adding that to the types that I have currently, because then I have to make sure I support usize for a lot of other parts of the generator. And this is again why I kind of want to separate signed types from unsigned types. And I think usize might be a third kind of type that I would want in that case. But again, the easy way is to just insert this cast inline here. So now if I run this again, it's still going to break the same way, but we should see that as usize has propagated to the output. So yeah, so now we will cast that. And again, I'm going to do that because this read address is going to be some other type, like a U32 or U128 or something. Hope it's not going to be that big. It won't be in practice, but in theory it could be, so we're going to support that. Anyway, this is basically what we wanted, except this else true again is going to be wrong because read data here you can see is a 1-bit signal. Okay, that one's actually correct. That's funny actually the way I did this. I think that's wrong though. Because read data, is the test wrong? Read adder, read enable. This seems like the wrong width. What do we do for this? For module mem. So when we create the mem, we give it a address bit width and then element bit width. I think I swapped these around and didn't update the test. I think that's what happened here. Yeah, this would be address and then the data. So that probably fixes that. Yeah, so now this breaks as expected. That makes more sense. Again, that's the kind of thing that the tests will cover eventually. That you can't, when you make a write port, for example, it makes you hook up these values correctly. But I haven't done that yet. I just have it as a to-do somewhere. But yeah, so now the read data is 4 bits like we wanted. And the write value also is 4 bits. Then we can see the enables are 1 bits. And then these write address is 1 bit, which is what we want. The read address is 1 bit for this particular memory. So yeah, so this is the correct interface. Again, we're missing fields for the actual memory. So we'll do the memory and then the read address. So I think that's what we want to fix next. And then we can fix this default value thing. And let's see. How do I want to fix that? Whoop. Sandeep, thanks for the follow. Almost missed it. Let's see. In sim, that's where this is. Yeah, so here we go over the registers that we implement. And I think I'm also going to make a small change here because we have the inputs and outputs like this. And I think I might want to add a new line here. And I think we're going to do the same thing for, instead of regs, we want mems. Right, and so here, we're going to get element type name. And we say that's going to be value type from bit width, and then we can do the mem dot, I think it's mem.mem actually in this case, because the way we wrap that up. Because it's this mem.mem, and a graph mem is the thing that we're going to get this off of, and that's going to have element bit width. That's what we want. Yeah, this we want mem here because we're going through all those, and then element bit width is private. Yeah, we want this to be pub crate. Fine. And then yeah, so here, instead of just the type, it's going to be this. And I think, again, we want to box that. We might end up making this a vector. Or maybe we do this and just have it as a box slice. I think I like that because then we can always allocate it off the stack, which I've had some issues with. So I think this is what we want to do. So then we have the mem. So we get the bit width, element bit width. And then the type name is the element type name. And yeah, this is mem.mem name because we need to generate, again, like this generates one for the value itself, the value of the register, and also the next value. And we're going to basically do the same here. So yeah, so we have this. Elements. and then the read one. And this one is simpler. So this is going to be for the type. Yes, so element type name, and then we also have let address type name is value type from bit width mem.mem.address bit width, and the name of that. And I think this is private still, so we need to make that pub crate here. That's what we want. And then, yeah. And then what did I call this? Mem read adder name. Like that. Yeah. So now we should have those fields. I think that will actually make the test build. And then I don't. Nope, because there's the incorrect value for the other one. The IR here, it doesn't capture like much type information. It literally just is like a semantic view of the code itself, like the symbols. So that's why I was able to generate code that returns invalid type here. So the compiler has to deal with that, which I think is the appropriate way to do this. But yeah, so now we have the elements itself here, and then the read address. And just like all other signals, if it's 1 bit, I map that to bool, and then from 2 to 32 bits, go to U32, from 33 to 64 bits, go to 64, and from 65 to 128, go up to 128. And in Kaze, we actually don't support more than 128-bit signals, and in theory, we could, but in practice, we don't. So right now, the compiler, or the API also has a bunch of checks to ensure that you don't create something that has more than whatever amount of bits. And I think that's also a good practical way to do this. So yeah, so now our prop is almost correct except this default value, which we'll fix next. And for that, we can do, well, we'll have to determine the type. So to do that, we can do let element bit, actually we can do element type is value type from bit width, and that will be mem.mem.element bit width. Toothmaw, thanks for the follow. I don't know why I didn't get the notification for that, actually. I just saw it on my screen. And then with this element type, we can match on that. And so let's say it's value type bool. Then we want a constant bool, and we're going to do true. And then it gives us all these ones that are not covered. And I know that this won't return signed values, so we're gonna not implement those, which is not my favorite thing to do. But until we have a better way to describe these types, is what we're gonna do. So for all of these cases, we're gonna do unreachable. And then for U32, we're going to have a constant U32, and we could do a std U32 max. And we'll do the same for 64 and 128. Oh yeah, and we need to do them here too. So I think that fixes that. I might actually write tests to test that this is the default value that we get. So that means it built correctly, but I haven't actually written the test, which we'll get to. But yeah, I might actually have tests that test that that's the default value we get, but I'm not so sure about that yet. I think I will do that though, because I need to test enable. So those tests will sort of indirectly also test that this is the value we get. hard to find. But yeah, I mean, this code looks good here, except that we're going to be missing the reset and positive clock methods. So we want to generate that too. So down here, I go over all the registers, and then I add stuff into this context. And again, let's just copy that for the mems. We'll start there. If I just do this and do mem, what happens? I don't know. So in this case, I know the second part's gonna basically be the same. We want to say that the read adder name is going to be equal to this next name. Yeah, actually, I think we need, because we need this read thing to behave like a register. Man, should I? That's a good question. Should I actually try to lower this to a register? I'm not sure if that's what I want to do. Let's kind of duplicate this logic first, because we need this read address to only be latched on the positive edge of the clock. So we needed to kind of do the same thing that we do with registers, where you have the current value and the next value. So actually, we need to go back in here and do read adder name and read adder a value name and next name. I'm gonna add to do here. Lower to register, which maybe we want to do instead, but I'll stick with doing it this kind of long form way first. Again, I think we'll copy this. Okay. So yeah, the read adder value is going to be assigned to whatever the read adder next name. And we'll comment out this part for now, which is where we want to perform the write. Yeah, so we need the read adder value name. And then we're also going to generate the read adder next name. Yeah, we don't need the bit width for that. Okay. Read adder name 354. Yeah, that's here. Read adder value name goes here. And then that's another important thing, is that in propagate, we also need to propagate the next read address values. That's going to be important. So that's again in sim. Yeah, also, we only iterate over the regs here. We need to iterate over the regs and the memories here. Yeah, we'll get to this. Or actually, this is exactly what I needed to do, isn't it? Because we need to compile a couple things. We need to compile the... Oh, did I get an expression for? There's a value in enable. We don't need to latch enable, do we? Ah, this is actually confusing. Yeah, I'm going to comment this out, and we're going to actually start writing the test, and we're going to see how this is going to be bad behavior, actually. I haven't described this correctly. I think this stuff is kind of fun. This is why we're doing like targeted tests at all of this stuff. Because it's so easy to get this wrong. Yeah, now we have this next and this adder thing. So you can see now there's a positive clock function to latch this read adder, which is what we want. And again, this is correct. But enable is not correct because right now, with it formulated like this, if this makes this enable not synchronous, it makes it asynchronous because this could sort of change at any time. And we actually want to latch the read enable and have the return data on the next cycle be whatever that latch value was. So the read enable, we also want to generate code like this too. And then it's looking even more attempting to lower this to a register. But I'm going to continue not doing that because I'm not entirely sure how that would look in the code. So yeah. So let's go ahead and lower to registers here. This is going to be read enable value and read enable next. Johnny Reed, thanks for the follow. It's been a while. I hope you're doing really well. I mean, I've heard the stuff you're working on is doing awesome. So really, I just think that's so cool. And I love hearing the updates from Chris. But yeah, I hope you're doing well. And I can't remember what it was that I saw you did on Twitter that I thought was really cool. Oh, it was the underwater preview. That was awesome. Let's see. Where were we? Yeah, we need to generate this register for this too. And I actually... So for the writes, I think we need to be... Well, we haven't done any of the write stuff yet, so we'll ignore that for now. Enable like this. And then, yeah, we need to store those. Yeah, that's what we need to do. Okay. And then in the compiler, we need to add more stuff here. So, yeah, this enable, again, is not correct. Because this actually needs to be... I'm actually going to call this cond later here, because the enable that we want to lower from that is going to be a different thing. So the conditional is not this. It's actually going to be a expref. And the name is going to be mem. What did I call it? Read enable value name. And then the scope is going to be ref scope member. That's what we want. There we go. And then Yeah, we actually don't compile enable here at all. Because just the expression that represents reading the value only needs to read that. And so we want to read with the current read value, and we want to use the read enable, the latched value. Okay, that's the code we want to generate. And then this is where we compile the address and next values. That's what we want to do here. So this is mem.mem. No, because we need, what do we need here? All the specific read ports, actually. So these state elements, did they capture the read ports? Yeah, I still don't think we have what we need for this part. So I'm going to come back to that one again. Because I wanted to do, yeah, this is the one I wanted to fix next to as well. So instead of the adder, I want to call these enable. And then see what we get from there. I think this is what I wanted. And now I don't think I generated fields for that. I didn't. I know that these are going to be Booleans, so we're just going to do this here. And read adder value name is going to be, yeah, these are the enable ones. That. Still, this is not going to be entirely correct, but we're getting there. Here. Yeah, so now we latch both of these values, and then the latched values are going to be used for enable and read. That's what we want. That's the behavior that we want when reading. As you can see, we haven't done anything for the write ports, and there's also no reset here, which I think is natural because we don't have initial contents, so I actually think it's good. And it was actually due to recent refactoring that it doesn't generate the reset if we actually don't have anything to reset, so this is good. However, we're going to run into all kinds of issues when we actually write the test. This is good. I'm actually going to continue, and I want to get to the point where we're actually testing things before I start implementing anything else, even though I know several things are going to need to be implemented. But I'm going to BRB for 2 minutes, and then I'll get back to this. All right, I'm back. And I know I said I was going to write the test before I do the implementation, but I actually realized what I needed to do to write the test, or to write the implementation, so I'm just going to do that. And it's not the read ports that we need to propagate stuff here, it's the write ports. That's kind of the key. So then what we're going to do is for the write ports, I think the write ports I just have as a tuple in this right now, and that's going to be address value enable. In mem.writeports.borrow.iter. Oops. Yeah, thanks, Jenny. Yeah, I appreciate it. Hi, Hannah. Man, it's been way too long since I've seen you guys. Field next to mem. Yeah, so here we're going to compile address. This is the wrong place to do this because we're not propagating anything. This is the code that needs to go in here. This is what we're doing. Oh, no, that's for reset. That's something else. This is for the pause edge clock stuff. Yeah, so we're getting the read value and read enable, and then before that, we're gonna do all this write port stuff. So actually, I think we actually want to generate some conditionals here, which should be fine. I think it's gen temp. Instead of push, and then you don't do assignment because you just do whatever expression you want. Is how I did this. And then this would give you an expression that represents, in this case, let address. It's going to be this. So we're actually going to do this. No, this is what we want. And then this needs to be compiled into this context as well. Write ports should be on mem. State elements. It's mem.writeports, and this is probably private. No, it's not. Okay, great. Yeah, easy. So then we have the address, the value, and then enable. And I'm also gonna do this just to make this a little bit nicer to read. Perfect. Yeah, so now we're going to compile each of these expressions in this context. And we should just generate locals from that. Now, I bet if I compile this, we just get some temps, and I kind of want to see that in the generated code. But we're not using them for anything. But it should still output those modules. So this should have had that, unless suddenly we got a new build. No. That is what gen temp should have done. So what did I do wrong? I don't know. Don't know what I did wrong. Isn't that what this does? So in one of these contexts, what did I call this? Oh, that's an IR even. So we have this assignment context, and here gen temp should have generated one of these. Did it not work? It did work. Then what happened? Did this just not reload or something? Okay, I'm not sure why this isn't working, but we'll just continue. Because this, yeah, and this should have had a write port too in the test. Oh, I think I know what happened. I think I never did anything in this function. Yep, that would do it. That's funny. Okay, so then this is easy, I think. Self.write ports dot borrow mute dot push. And here we do address value enable. I think that's it for this. The way I have this implemented. Okay, so that should actually generate those temps. That makes sense. And then with that, here we go. So here's the temps that we have to generate that. So one of these is the value, which you can see is masked to that number of bits. Somehow we got another thing from that, but that's fine. And then here's the address. And then the write enable, which are just these inputs. So that's cool. So then we need to use these to actually write to the memory. Now, one of the things that the IR doesn't support is a conditional like control flow, because the only kind of code that I've generated so far has been assignments, which either assign to a local member or a member of the struct or to a temporary like this, depending on the scope. So to generate something like this, I might get a bit cheeky and do a ternary expression where I always assign to the memory location and then I just use the previous value. If that's not what I wanted. Is that what I want to do? I mean, it isn't really what I want to do. Maybe that's the best way to do this, because like I said, I only have assignments here. Let's see. Assignment is private. I think I build it here and then push it in there. I could maybe like, no, because I don't want to have like scopes here. That's not what this is supposed to be. All right, I'm going to do it the cheeky way. It's going to be great. And I think what I can do is element is expref, and this is going to be name is mem dot also this is not, that's, wait. It's not a ref. That's what we want. We want a array index. And this is going to be target is a ref, and then the index is going to be box new address. And then, that's gonna give us a reference to this particular array element. And then we need the scope here, which is gonna be ref scope member. And then with this element, we want to do this. So we're going to say positive clock context dot push. And here we're going to have an assignment. And the target scope, in this case, is going to be member. And then the oh no, because assignments, they also, the left-hand side is only a name of a variable. So we have to extend assignments anyway to be able to, I'm not super pleased with this. Okay, I might change assignments so that instead of target scope and name, they have a ref. And then expression.ref can also just delegate to a ref struct, which has a name and a scope. And then that ref is either going to be, because we don't just want the name, a ref might be an index. Oh, this sucks. I don't like how this is turning out. You know, we could also go in and for assignment, we still want to be the expert here. Maybe we do this. Maybe we do an enum assignment, and then we do a target. No, we do a ref. And then we have a scope, target scope, and a name, which is a string, which I think is the same stuff ref has here. They swap it around, so we can swap that around too. Name and a scope. Or we could have an array index. So this is looks really similar to the experts here, but I think this is what we want. And then an array index also is going to have a name, which is a string. It's going to have a scope, which is a target scope. It's going to have an index. And that's actually going to be an expression. I think that's the way we want to do this, because like I still want to restrict having the left-hand side not be generally an expression. It wouldn't actually matter as long as we do all these correctly, as long as we always use refs, but yeah. I think this is what I want. And then we need the expression in both cases. And then for this, we might also want assignment target. And then maybe we do it this way. I think that's how I want to model this. I think I want to do one more thing, actually. Maybe. Kind of annoyed about this. Because I'm looking at some of this logic that might end up being duplicated. Because we have duplicated members here. That's sort of the idea. So maybe I have pub struct assignment target ref. I do this. And then have I just duplicated like this kind of logic because I don't have... I might as well just use expressions for the target, shouldn't I? Because in this case, we would get like all of this for free. I normally don't like doing that stuff just because the data like looks similar. But I'm actually thinking that this might just make a lot of sense. So in that case, it becomes this. We have the target, which is an expression, and then the expression, which is an expression. And then how does this code look? I think it looks like this. I think we do self.target.write because we already know how to write expressions. And then append equals, and then the value. That looks pretty good to me. Let's continue with this. I can always back out of these refactorings. This is the kind of stuff that I actually really like doing in Rust because the compiler's just telling me what to do the whole time. And I actually trust that it's going to lead me in the right direction. So I'm quite okay doing this. Except now all these, every time we have an assignment, we're going to say target is expression, and this is going to be scope target expression dot ref scope local, and then the name. Name is in the other order now, which is target name dot clone. Here, let's just call name in this case. That goes away. Yeah. I think this is what we actually want. And then I think we can do one other change, and that's right now I have two different scopes. There's ref scope and target scope, and target scope just goes away. And then we have ref scope. And I think ref scope we want to just call scope now. Because I think that's the only place they're ever going to be used. Actually, what do I do first on these refs? Name and then scope. Yeah, then let's maintain that here. I think this, yeah. Maybe it's not that bad that we have these. Oh, yeah, this is an easy change because we just go through all the ref scope ones and we do scope. And then everywhere we use ref. No, that's still going to be correct. I think it's just the top level code actually that creates assignments, which is the stuff in here. And then now the target needs to be different. So the target is going to be exper ref. It's almost always just going to be a ref. And then the name is name.clone, and then the scope is scope member. And this is basically going to be the same for this one, which is going to be reg.nextName.clone. Is that MRAZ or Mr. AZ? Mr. AZ? I didn't quite see it, but thanks for the follow. Really appreciate it. And then here also. And here. Yeah, same thing, I guess. I do kind of like the symmetry. You have the left-hand side and the right-hand side thing, so. Uh-oh. What was that? I seem to have done that wrong. Just copy this again. Yeah, so here, the name needs to be reg.valueName.clone. And this is the same, I guess. Yeah, because this is the initial value, and then this is the update. So this makes sense. Yeah. Okay. And yet ref scope doesn't exist anymore, so that's just scope. Also, do I have clone implemented on expert? Yeah, I do, which is nice because then we can do, since this ref is going to be the same, we can actually memoize that too. So we can say let's target is this stuff. We need to clone it here. And then this target, it just looks like that. Yeah, so this refactoring is actually kind of nice, I think. And then this one is the one we were working on. So now we have the target. Is the element. And the expr is going to be ternary. And we have cond is box new enable. When true, it's going to be the new value. So box new value. And when false, it's going to be the element. Okay, and then here for the target, we're going to have this other value here. And basically same here. And that's going to call target in this case. And now it says target and expr are private, which is fine because we can just make those public since we're creating these. That might work. Seems to be a long time building. We might have messed something up here. Just waiting for this to blow its stack if that's what's happening. It's a bit odd, actually. This is probably just outdated right now. Yeah, it's taking a while. Can remove this directory, probably because I have it open here. Yeah, it might have just been dumping a bunch of stuff to my hard drive. My guess is that it isn't, but it might be. We can see if it's actually made this file or not. Okay, so it has actually made the file. Then why is it just taking ages? So we just ran this, right? Is it having trouble building this or something? That's weird. But yeah, here we have this assignment. So it did actually generate this, right? But then I don't know why it's taking a super long time to actually build the test. It's a bit concerning, but okay. So, yeah, here we got the write address, and this is going to be, yeah, this is that input. Yeah, that makes sense, because it didn't need to propagate to anything, because the write address is just that value. Is that actually what we want? I feel like it's not. I feel like we should actually, similarly to how we sort of register these read values, I think we should do those for these write values as well, and have next values for all those. Because I feel like positive clock shouldn't be doing a lot of propagation, and right now it's really simple because this just refers to the input. But this is an arbitrary expression. Like even this masking here is just proof that this is actually propagating whatever we would throw at that, and I want all propagation to happen in prop. So to me, it seems incorrect that that's actually being done this way. Also, why the hell is this taking so long to build? That makes no sense to me, you guys. What did I break? Anyway, for the value, we have the left-hand side is equal to if enable, then we have the new value, which is this masked input, otherwise the current value. So this looks good at least. And it looks like all the other assignments are fine. Ooh, not quite actually. Because these should be lets. I'm gonna kill this again and fix that. Maybe stuff just works out. That is because in here, I just wrote this left-hand side for the target. Ah, that is slightly different here, actually. Because all these expressions were only meant to be used in an expression context, so I never... The problem is we need to write out let here. And I don't want to have some stupid conditional logic that does it here. Maybe I just do that though. If let can I destructure like this with if let? We'll do this, right? Scope like this equals self.target. If true, we can do match scope. And this will either be scope local and scope members do nothing. Guess that's what we could do. Yeah, so that apparently blew up the compiler somehow if we didn't do that. That's kind of funny. Okay, so now we get what we want, but I think this is kind of ugly, but it might still be the best option. I don't really know a better way to do this other than declaring all of them first, which I guess we could do, because we don't know the expression types at this point in the compiler, so really this is a to-do for now. At least it worked. But yeah, I still want to kind of like register those inputs, and then it gets more and more tempting to lower these to registers, but I think the compiler assumes that there's actual registers. It might actually be a good idea to, maybe that's what we want to do. Maybe we want to, at this level, register the inputs. That seems like a really good idea, doesn't it? And same with this read stuff. We could actually create registers in the graph at this level. Guys, I think that's the solution. By the way, I'm just really happy on a completely other note. Like I've been working on this and a couple other compiler-y things in Rust, and I always have a great time when I'm doing them. And I'm really happy that I'm able to capture some of this on stream, because I feel like I basically never have. Whenever I'm doing something compiler-y, I never end up doing it on stream, but I'm happy to do that today. Desu use that's a really good suggestion, actually. Let's refactor that to look like how you suggest as well. By I hate this kind of conditionals, I actually meant this kind of conditional logic. But if we have to do it anyway, I am happy to write it in a better way. Or can we destructure? Because this is like 2 levels of destructuring. Because scope is part of the thing. Otherwise, I don't think we can do it that way. Just because scope comes from this thing. So I think it has to be nested like this. Can we do that? Okay. So if we match self.target, right? Because we don't have scope here because it comes from here. Yeah, I don't think this will work. If scope came from out here, I think that would work. But otherwise, I think it has to be nested. And then I like using if-let here because this is the only case we care about. Yeah, I think we have to leave it. But yeah, I think a lot of code will kind of go away now because we're not going to explicitly register all this stuff. So in state elements, we don't need like any of this stuff, do we? Also, this is wrong too, because this assumes you only have one read port. I just realized. Ugh. Okay, I think this is going to arrive at a really good solution, but we have to do some really roundabout stuff here. I'm not going to stream for too much longer, but we'll see how far we get. because self has a name. Okay, so we'll do this. We'll do name is self dot, actually we'll do format. So I've been using this double underscore convention for generated names. So that's kind of like reserved stuff. Because it's possible to give some of the stuff a name that would conflict with whatever name we give it, but this double underscore at least allows us to come up with specific stuff here. So we'll do mem read port. This will be name prefix, because we need to create a couple registers. Equals self.module.reg. And actually, in Xenowing, I haven't moved this to the compiler, which I want to do. But in Xenowing, and I totally shamelessly took this from Chisel, we have this reg next construct. Yeah, exactly. Well, this is for the generated code anyway, so I don't think namespaces would work there. But yeah, anyway, we have this reg next thing that can take any signal. And currently, because it's external to the API, it has to take a module too. But it would normally just take a signal and you give it a name, and then it returns a register where you only drive the next value of the register with itself. And I think that's exactly what we want to do here. But I haven't moved it into the library proper yet. It's only in that one usage. So we need to make a module here, and it's going to be format for the name. Address. This will be name prefix. And then reg takes 2 parameters, because I'm actually going to open this again. That was an easy way to see that. Where was it? Where was it? Here. Yeah, the name and then the bit width. That's what it is. And so for this, the bit width is self.address bit width. And then address.drive next with address, this address. So we actually need to differentiate those. And then the read port output is actually going to use this register for the address. Dot value we have to do. Using reg next, we wouldn't actually have to write address reg here. But we'll save that for another time, moving that construct into the language here. Although actually what I could do, and what I think I'm gonna do, is just keep this internal here. And then, first of all, we don't need the module here, because module can be next.module.reg, which is kind of always the point. And then address reg becomes address. This one at the bottom here, we don't need to take the value anymore, because this is going to be address drive next, or reg next, I think I called it. And then that just takes the name, I think. Oh yeah, and right now I have it. I want to make this a member of Signal, which I should just do, right? Because it can be a private member. Oh, that's ultimately what I want. I'm not sure where to put this. I'm just going to put it at the bottom, I guess, of the signal impulse. Yeah, and now instead of next, it's going to be self. Yes, and then A is already in scope. Data-less-V, thanks for the follow. All right, so this is cool because now, now that's private because we can make it pub crate. Pub super might be enough here. Yeah, I think that's what we want. Yeah, nice. So then we can do that for enable as well. And I think it's kind of nice when you can like lower stuff on the API level like this, because then the compiler never even needs to know that this is like behaves like registers. The compiler will just consume regular signals. I think that's fun. And then yeah, that's good. And then we'll do the same here. So now we have address value and enable. And that should just work. And now we're looking good. So now I think we just need to remove a lot of code in the compiler. A couple things. I just want to double check that. Let's see. Validation doesn't do anything with this. That's fine. I don't think there's anything in here that needs to validate anything. Yeah, this is not what I meant to look at. Actually, I meant to look at state elements. First of all, we're going to get rid of all this stuff for the memory. Now the memory is just the memory itself and then the name. Yeah, so we're actually not done here because we need to keep track of read ports. We'll get to that. Yeah, we'll get rid of all this stuff here. Just inline this for now. Leave this as is, but I think, yeah, I think we actually won't have enough to go on for this. Luckily, we don't need any of this stuff here because all that's going to be generated from the registers. So that's good. But it's this stuff. No, these ones we also don't need. Because again, we just have the elements themselves. But the code that writes it, oh yeah, that's fine because we already memorized the write ports. We might be good, you guys. Maybe not. Read enable value name. Where was that? Down here. Mem read port. That's fine because from here, just want to look up the order of this again. We had mem address enable. And we're going to do the same thing because now we have these. And before I changed all these to be these refs, but actually now they are these values. like I had them the first time. And actually, yeah, we will call this con because let con is self.compile signal, and that'll be enable. And I think that's in the same context A, like that. And then the index is going to be, yeah, I'm actually going to do it the other way. Where we do instead of con, we're going to do enable, because I like to just take these and do like address here. What's happening here? Oh yeah, this is the when true thing. It's the array index, yeah. So we do want that, and then the address is just going to be this. The index is going to be box new address, and this element thing is correct still. Yeah. This is good, you guys. Although it looks like we have some unused stuff. And I accidentally did something that wasn't snake case. Ruh-roh. How? That seems wrong to me. Oh, it doesn't like this couple underscores after reg like this. Okay. That should be an easy fix. Yeah, that's what it is. Oh, yeah, because the reg already adds an underscore. Okay, but that's easy, because then I can just not have underscores here. Is that not enough? There's probably an underscore because of reg there. I'm actually going to do this. So we have the right port like this. And then it's still possible that we create a register that ends up the same name as this, but actually that's only possible. Like I think I have a to-do for name checks to make sure that a name is like unique in a given context. And that's like the one thing in the API that I'm just not doing anywhere that I want to do in a lot of places. And that's what would eliminate these kind of cases. So I'm actually going to kind of ignore that one for now. But yeah, so now we have these read port enable, read port address, and then the write port address value and enable. And if we look at the positive clock stuff, we can see that we get the register stuff works great. The propagation stuff works great, because it just uses these values. That looks good to me. And then this one here, temp0 is this new value. The order here might actually be kind of important, but I think it's actually correct. So we update all the registers and then we write to that new value that we did just register, which is what we want to express. And then we also read from, yeah, this addresses the new value. I do think this is what we want. So that's kind of cool. That just pulled a lot of weight for us. So that's nice. And we have another excuse to make that regnext construct a proper thing in the API, which is that we're using it here. All right, I'm going to call it quits for tonight. We haven't gotten to any of the testing, and there's some more stuff here, but I'm gonna go ahead and push this. I've got this commit that I just keep amending. That looks good to me. It's on a branch, and then we'll just go ahead and force push that, and then I'll continue on that later. But so far, I think this is great. Yeah, sorry, Lord DeCapo. But I'm really happy with that implementation. I think that's really nice. That everything just kind of gets handled that way. There might be other, I actually don't know what other contracts might work like this, but I mean, it makes sense to implement it this way too, because we do want to kind of register these values, and then on the next clock edge, we want to actually use these. So yeah, again, I think this is the right way to do this, because the behavior of the original one was like that. Although I will admit, we do have some extra storage here that we don't need, because technically we only need the next values, since the only times when like these address values are used for like the write ports is here within this same function. The read ports is the opposite. The read ports, we actually do forward the value to this propagate function. But I think that's okay. I don't think it hurts to have these extra fields here. At least not for this implementation. Anyway, thanks guys for hanging out. I'm going to go ahead and leave, and I'll see you next time.